All right, guys, so we were trying to answer the question of maximum power transfer, namely, if you happen to have a linear network operating under sinusoidal steady state, then what kind of load can you add to the terminals of the network in such a way that you get the max amount of power going from the linear network and being delivered to the load? We're splitting this into a few steps, but what we had last time was we found that so this is max power transfer. We had found that the real power was actually a function of two variables. It was a function of the load resistance and a function of the load reactance. Um, and we had determined using calculus to say to maximize the real power, two conditions needed to be met. The first was that the first derivative of the power with respect to the load resistance should be equal to 0. And there are going to be some conditions that come along based on that requirement. And that the partial derivative with respect to the load reactance, that should be equal to 0 as well. And we had concentrated our efforts in really finding out what that actually was. And what we found was that the power was equal to the Thevenin voltage squared times the load resistance divided by the Thevenin resistance plus the load resistance, 20 squared, plus the Thevenin reactance plus the load reactance squared. And this is where we had actually left off. One special note, and I caught myself doing this interchangeably. Keep in mind that this Thevenin voltage, because it was the RMS voltage, keep in mind that in terms of our notation, this was the same thing as the effective voltage. But keep in mind that this is constant, it's fixed, it's something that we have no control over. So now what we want to do is we actually want to split this into two parts, find the partial of the power with respect to the load resistance set equal to 0, and find the conditions under which that happens. Same thing with the partial of the reactance set equal to 0, and find the conditions that comes along with. So we're actually going to have two partial derivatives. Let's start with the first one. So this is going to be part 1, and it's going to be to look at the partial of the real power with respect to the load reactance and set that equal to 0. Now, the reason I chose this first should become abundantly clear, and it's because notice that that load reactance appears there and only there. It's nowhere else in the equation. However, if you actually take a look at the load resistance, right, notice that the load resistance appears in the numerator and in the denominator, thereby complicating our partial derivative. So let's go for the low-hanging fruit first. Let's take the derivative that's the easier one of the derivatives to take, and then set equal to 0 and see what that does for us. So here, the partial of the power with respect to the load reactance is the partial with respect to the load reactance of the magnitude of the Thevenin voltage squared times load resistance divided by the Thevenin resistance plus load resistance plus the quantity squared plus the Thevenin reactance plus load reactance quantity squared, like this. Right? Notice that this whole thing, this partial derivative, it's not going to affect this and this because they're constant, right? Again, the only time this variable appears is right there. So I'm going to rewrite this for simplicity I can pull this part completely out of the partial derivative. And then I'm going to take the partial derivative of, let me rewrite it in this way. Thevenin resistance plus load resistance quantity squared, Thevenin reactance plus load reactance quantity squared. And this whole thing is being raised to the -1 because the whole thing was in the denominator. So notice that I can actually use the chain rule here. Right? So according to the chain rule, well, one of the things that I'm going to do is I'm going to have to pull down a -1, and then I'm going to subtract 1 from that, and then I'm actually going to take the derivative of the inside. Now, keep in mind that the derivative of the inside, that part's going to go away, and I actually have to use the chain rule on that term. So there's a lot of things that are actually going on here. Right? So let's actually form that calculation. So we have the -1 that's going to come out. We have Thevenin voltage magnitude squared times R sub L. Now I'm going to again subtract 1 from this monstrosity. So it's the Thevenin resistance plus the load resistance quantity squared plus Thevenin reactance plus load reactance quantity squared. I have to subtract 1 from the exponent. And then I'm actually taking the partial derivative of the load reactance of these two added together squared plus these two added together squared. Notice that this derivative is going to completely kill this one. And here again, I can use the chain rule and say that just this part, and I'm going to do this in blue so that you can really keep track of it. Only the derivative of this part, well, it's got to be 2 x Thevenin plus xl times the derivative of the inside, but the derivative of the inside is just 1, right? So let's clean up this huge thing. It's a horrible thing, but the partial derivative of the power with respect to the reactance, and let's keep track of these terms very carefully. We have the minus Thevenin voltage squared times the load resistance. We then have this term in the numerator. So here we have 2 times the Thevenin reactance plus the load reactance. We also have this monstrosity of term. Notice that it's being squared, and you can keep that in the denominator. So here it is the Thevenin resistance plus the load resistance quantity squared plus the Thevenin reactance plus the load reactance quantity squared, and this whole thing has to be squared. Hooray. Now, notice that this we actually have to set equal to 0. Now, there's 3 ways in which this can actually be equal to 0, right? So here, the solution to this is, well, the magnitude of the Thevenin voltage squared, well, that could be 0, but we have no control over that, right? So this solution, which is our first solution, right? This one right here, I'm going to cross it off. See, this is rejected. We don't want that. The second solution, if that's actually going to be 0, is, well, this could have been 0. Similarly, the load resistance could have been 0. Right. So here the second solution the load resistance could have been 0. Usually this is not the case. This one right here is also rejected. If the load resistance is actually 0, what that's actually going to lead to, if you go through the mathematical steps, is that's going to lead to a minimum power transfer, right? If RL is 0, you're not maximizing power transfer. Well, you're getting 0 power. Why? Because that would be 0, which would mean this is 0. We don't want that. So when RL is 0, you get a min, not a max. That's why we're rejecting it. The last condition for this actually being 0, right, is there's a third term in the product. It's this part. That could actually be 0. So here, what we actually have is the Thevenin reactance plus the load reactance. That could be 0, which means that, again, if the load reactance is equal to minus the Thevenin reactance, this is the condition that we were looking for. Let me actually go back. Let's not actually put this in red. Let's put this in green. This is okay. This is our condition for max power transfer. Now, we took a look at what happened when we actually take the partial derivative of the power with respect to the load reactance and found that condition. We have a second part that we want to take a look at, but we'll leave that for the next part of the video, and then we'll assemble all the pieces.